So let me start with a recap from yesterday for everyone who was a little sleepy or something. So what happened is, so the setting is that I have a three-manifold and an Anosov flow, or the pseudo-Anosov. If you're some expert on that, you can insert that all into this framework, but if not, don't worry about it. And from that, I construct, so what do? You lift it to the universal cover, you quotient by orbits, and you get something that's topologically a plane with two transverse foliations. And because everything came from something down on the manifold lifted to the universal cover, it inherits an action of the fundamental group of your manifold that preserves each of these foliations, right? Sends leaves to leaves. And the situation we're interested in is in the case where these flows are transitive, because that gives you richer dynamics here. In that case, we call this an example of an Anosov-like action of a group on a plane with foliations. So now, that's our example of a group. And the theme is to study, just in the abstract, Anosov-like actions of groups. They don't have to be three-manifold groups, just of groups on bifoliated planes. Because these are interesting examples of discrete dynamical systems that have some kind of hyperbolicity type behavior locally. As well as being interesting in their own right, you can hope to prove results about Anosov or pseudo-Anosov flows on manifolds using this kind of framework. And so what's an Anosov-like action? It's something that satisfies these 5 abstract axioms that were sort of essential properties that apply to this example, such as from local hyperbolic behavior. So if an element has a fixed point, then it contracts one foliation and expands another. There was a transitivity-like assumption which said that there was some dense orbit. We had an Anosov closing lemma-like assumption which said that the set of points on the plane that were fixed by various elements, as you vary over all the elements of your group, that's a dense subset of the plane. Right. And then 2 others that just sort of capture the structure of these foliations generally. Okay, so that's sort of where we were at. And so our goal really is to kind of prove new results about Anosov flows using this framework, but you can start by, reproving known results about Anosov flows in this more general setting. So the first one that Thomas advertised was this. This is still in the yesterday board, which is why I wrote it before, is this trichotomy theorem, which, while originally proved for Anosov flows, Barbeau's proof translates pretty well. Just to, you kind of reread it and see that it only actually uses the dynamics of the group acting on the plane in these axioms. And you can prove it from the axioms alone to show that if you have an Anosov-like action of some group on some bifoliated plane, then one of the following 3 pictures holds. Either your plane is trivial, and actually in this case, this corresponds to your action is by affine transformations of this, standard R2 with its 2 foliations. That comes from kind of the local dynamics assumption and Solodov's theorem. Okay, or this picture can happen where your plane and with its 2 foliations is homeomorphic to this kind of diagonal strip. Geodesic flow is an example that gets this behavior, but there's infinitely many other examples. There's lots of other examples. This is called skew. Or if these are not the situation, then, the leaf spaces of both foliations are non-Hausdorff, and it's this hard to describe mess that you get. Okay. So, very good. So that's one, example of reproving a result. Another thing, so I'm going to state as another sample of why this is an advertisement of why this is interesting or exciting is that you can do new things. So let me state a special case of what motivated this whole theory of Anosov-like actions on bifoliate planes, like why we're advertising this as a mini course. This is a joint theorem of Thomas and myself and Stephen Frankel. Okay, and I'm going to state a special case so that I don't have to lie and I don't have to explain more words. So this is the special case I'll state right now. It's suppose you have, I don't know, let's say a hyperbolic three-manifold. Okay, I constrain its geometry somehow, but really what I care about is it's actually it's topology more than its geometry. I don't want embedded tori for this. We know from earlier work I did with Jonathan Bowden that there exist examples of hyperbolic three-manifolds that admit, I don't know, 20 million distinct up to orbit equivalence Anosov flows. So it is an interesting and difficult classification theorem problem to say, like, well, what are the invariants that distinguish them, even if you fix the manifold? Okay, so in this setting, I don't know, or in general, I could say I'm going to let fancy P of a flow denote the set of free homotopy classes of periodic orbits. Right. So the set of, now I'm thinking of gamma as a like conjugacy class in the fundamental group of your manifold, so that we didn't care about orientation yesterday, we won't today. Either gamma or its inverse represents a periodic orbit. Okay. So that's just set up the theorem. The special case of the theorem is in this hyperbolic setting, which says that if I have two flows, if phi, psi are transitive Anosov flows, and their periodic orbit, just a set of free homotopy classes you see, just happens to agree as a set, then these are orbit equivalent by map isotopic to the identity. So they are isotopically equivalent. Okay. And obviously the converse is true, right? Like if they happen to be isotopically equivalent, well then they have the same free homotopy classes. So this set becomes a complete invariant of isotopy equivalence. And if you say these agree up to some automorphism of pi1 inducing some map on its conjugacy classes, then that gives you a complete invariant of orbit equivalence. Yeah. By definition, because we said, yeah. That's why we're cheating. Yes. You thought we proved something false, but we didn't. We just observed it in the definition. No. Okay, and where does it? What is this? This is a theorem about flows, but it follows from a theorem about Anosov-like actions on bifoliated planes. So here's a theorem. Suppose that I have two actions, so rho 1 and rho 2 of G on some bifoliated plane. I don't know, I'll write homeomorphisms of P, F, plus minus. Now these planes are allowed to be different a priori, and the foliations are allowed to be different, right? One of these could be, I don't know, like askew, and one of them could be crazy. But I will assume that they are non-trivial. Meaning I exclude this first case that we totally understand the actions are by affine transformations, so this gets quickly thrown out of the things we have to study. Let me adapt, I guess, my same convention as before. I can let, I don't know, curly P of rho I just be the set of, well, under our correspondence, periodic orbits, right, corresponded to elements that had fixed points on the plane, because the plane is my orbit space. So that's the set of G in my group, so that rho I G fixes some, possibly several, possibly infinitely many, but at least one point in the plane it's acting on. Okay. Okay. Then, oh wait, we want to assume something. So we're going to assume one of your planes, I don't know, let's say P1 or something. This is the hypothesis you're supposed to not understand right now, just like why I restricted to hyperbolic 3 manifolds there was a mystery, okay? So this is the mystery part to be explained by the end of the mini course. P1 has no weird and bizarre feature that we call a tree of scalloped regions. Okay. To be defined. It's something you see in your foliation. So if these sets of elements that act with fixed points happen to agree, then your planes were actually the same planes with the same foliation up to homeomorphism. You had to say it wasn't that one was skew and one was not. They are the same plane with the same foliation. So I don't know, maybe I'll say P1 F plus minus 1 equals, or homeomorphic to, meaning I take a foliation to another foliation by this homeomorphism. But I'm allowed to swap the F1, the one I labeled arbitrarily by a plus with the one I labeled arbitrarily by a minus there. That's fine, but I take the pair to the pair. And better than that, actually, there's a homeomorphism that conjugates the two actions. And the rho I actions of G are conjugate. Okay, and this theorem implies that one, modulo this comment about scalloped regions, is a test that you were listing yesterday about how periodic orbit, sort of knowing actions up to conjugacy determines the flow up to orbit equivalence. Okay. So that's supposed to be some advertisement of one version you can care. We can prove a new theorem about invariance for the classification problem for Anosov flows using this action on plane thing. And so what's my goal is today, I want to just prove some of, some basic structure theory for Anosov-like actions, give you a sense of how to work with this, and with the goal in mind of by the end of the next lecture, giving you some tools to so you at least believe how this works, and to explain this weird hypothesis also. Okay. So I'll have to talk about what these planes can look like too. Somehow admitting an Anosov-like action, as you can already see by the trichotomy, it constrains sort of the topology of these transverse foliations, the pair of foliations already. Any questions before we launch ahead? Okay. Right, so I need one more vocabulary word from last time. So that was what differentiates the trivial plane from the skew plane, right? That was the presence of lozenges. So in the trivial plane, right, every leaf of the blue foliation intersects every leaf of the red foliation, right? Here you have some blue leaves that don't intersect red leaves, and then you have some blue leaves that almost intersect a red leaf, meaning that I have a sequence of leaves that intersects this particular blue leaf in my leaf space, and then you know, they limit onto one that just barely doesn't. So that structure of just barely not intersecting is called a perfect fit. And when you have a nice arrangement of them, like this, this structure in a bifoliated plane is called a lozenge. And the 2 points of actual intersection are called the corners. Well, that one's called a corner. Here's another corner. Okay. Great. Okay. So the first thing that I want to prove as a test case of, like, I don't know how to prove things from axioms or whatever, and is about identifying corners versus not corners. Okay. Okay. So first definition, I don't know, maybe just definition or notation. So the setup here is that I'm given some Anosov-like action on a bifoliated plane. Okay, and I want to. Yeah, yeah, just purely abstract group acting on plane. Sorry, for the time being. Yeah. I mean, yeah. So you can, if you have examples in your mind that come from Anosov flows, those are the examples you should think about, right? But it's purely some things that satisfy some list of 5 axioms. That's it. Okay. Yeah, and so this is now a picture that you abstract. You forget that there was a flow. This is a picture that's of something that can happen in a plane with 2 transverse foliations. Great. Okay, so definition, I don't know, let's call non-corner fixed point in my plane is exactly what it sounds like, is some x that is not a corner of any lozenge, such that, you know, there exists some element of my group that fixes this point. Okay. Here's a.
It just say for the rest of the talk that G is never going to be the identity.
Oh, yes. Okay. Otherwise, every point is not, yeah. I'll forget to write this every single time, but if there's some statement I make that would be trivial, if you said, well, what about the identity element? No. Yes?
Do you have examples of Anosov-like actions that don't come from?
Yes, that's a great question. So we can build them in this setting and in that setting that are certifiably, we can build actions of things that are not even 3-manifold groups, so it couldn't have come from an Anosov flow, if you like. Here it's tricky because, so in the skew and the trivial case, you can kind of say what dynamically, what kind of subgroup of transformations it should be, because your plane is simple. To build an example here, I suspect there are examples that don't come from Anosov flows, but to certify that I have now built a weird non-Hausdorff leaf space bifoliated plane with an action of this group that checks out all our axioms, but has, like, didn't come from anything remotely geometric, that's tricky. If you have an idea, that would be nice. Yeah. I mean, the problem in the other direction is also, let me say something I was going to state as an open problem later, but the problem in the other direction is also interesting. A rigidity theorem, you would want to say, well, if I add axiom 6, 7, 8, and 9, now anything that satisfies this list of properties does come from an Anosov flow. Like that would be quite cool, right? There should be some nice list. Yeah?
One of the conditions admit not separated leaves from below but not from above, you can get that kind of...
I'm not sure off the top of my head of whether that will ever happen for an action that satisfies our axioms. I don't have a proof or disproof. But yes, that would be a good strategy. Okay, okay, so here's a proposition. How can we prove something? Let me start by stating something that sounds, kind of weak, but we'll get something much stronger soon. So I suppose I have some Anosov-like action. Okay. So, and suppose that I see in my plane two adjacent lozenges. Okay, so what do I mean by that? That means that, I have, this is my perfect fit point. Well, I guess I'll draw them in my two colors as before. All right, so you're imagining my red foliation is completely vertical, and the blue one, I have various leaves here that like limit onto these two at the same time, right? So it turns out actually that this happens every time you see non-separated leaves in your plane. You'll see actually two adjacent lozenges like this. Okay, but for the moment, suppose I just can see this picture. This is something that does not happen in the skew case, but does happen in case 3 every single time. Okay. So suppose I just see this configuration somewhere in my plane, then the set of non-corner points, non-corner fixed points in P is dense. Okay, so that's this is saying as soon as you're sort of in case 3, you have something very different from the skew case. When I have if I have, every point here is a corner. And so here, if I have an Anosov-like group action, I have many fixed points of elements that happen to be not corners of anything. Okay, so let's prove this. I'm going to prove this just using the axioms, which I'll remind you what they are. Okay. Okay, so first I'm going to use axiom 3, which was like the Anosov closing lemma thing. It says the set of fixed points of elements is dense. I don't know about corners versus non-corners, but at least the fixed points are dense. So that means at least there exists some element with a fixed point in this lozenge. This is an open subset of my plane. There exists some G fixing some point in, I don't know, maybe this lozenge is L1 and this one is L2. Okay, okay, so there is a red leaf and a blue leaf through this thing. And up to replacing G with its inverse, I could assume it, contracts in this direction and expands in that direction. That was my axiom A1. All right, is how I drew this picture. So let's see what happens if I now apply G and look at the image of L2 under G. Okay, so what is G of L2 now? It's going to be, so let's see, this leaf intersects here, so it's going to have to intersect somewhere further along according to the dynamics. Let me get a new picture to draw. I'll draw its image, I don't know, in green or something like this. So this blue leaf goes to another blue leaf, and it gets contracted towards this attracting point, so it's somewhere here. all right? And with its new perfect fit being somewhere way over there. And the bottom one is going to be something, you know, like this. And then this red leaf gets expanded out. So I'll see this. That's where the corner went. And I'll see something that looks like, oh, I need to make this longer. See a corner. All right, so that's what G of L2 has to look like, just, well, in relation to these other lozenges already sitting there just by the dynamics. Okay, and now I claim actually that A1 was just how I drew this picture. I claim that actually inside of, what do I want? L1 intersect G of L2 contains no corners of any lozenges. All right, so this gives me a whole open set in here where I claim you'll never find a corner. So let's prove this claim. I'm going to pick a point here and say, could it possibly be the corner? Well, it has some kind of leaf of my one foliation and a leaf of another foliation going through it. And we just have to kind of check every quadrant and see what goes wrong. So could this have been a corner like this of a lozenge with a perfect fit here? Let us test. Well, what does that mean? It means that, you know, somewhere off out in my plane, I would see also its other corner here. And this leaf, this red leaf and this blue leaf, have to cross each other, but of course I'm not allowed, the blue leaf is not allowed to cross this blue leaf, and the red leaf is not allowed to cross that red leaf, because I'm foliations, and so they cannot possibly intersect and form another corner, right? So this direction here is bad, and sort of what happened, or maybe I can even localize the problem, was that I had this perfect fit here, of a blue and a red, and that prevented me from completing out this lozenge, right? So this guy here was the problem. Okay, but then if I start checking every other quadrant, right here, I see the same picture, right? Perfect fit will give me a problem there. Here I have one that's also going to give me a problem to try and stick a lozenge over there. Here I have one to stick a lozenge over there. I'm very sad. There's no way to fit that into that picture. All right. So the proof now is check each quadrant. You can formalize this to like what is a criterion for there can be a lozenge going off in that direction, but it's exactly what I just did, sort of by hand. Okay, great. So that establishes the claim, and so now I have found an open subset on which there are no corners of lozenges, okay? And one of my other axioms was that the set of fixed points is dense. So I have found, thus, we have open subset of non-corners. Let me do this in the right order. By our transitivity assumption, meaning there exists a dense orbit. Which one was that? I wrote down a cheat sheet for myself, but maybe not enough of it. A2? The substitute for transitivity implies that the set of all non-corners is dense and open. All right, and so when I intersect this with the set of fixed points of elements, which is some dense subset, so that's using A3 again, this is now a dense set. Right. Okay. Okay, so here is sort of a sample of, from the axioms plus some little assumption on, you know, a piece of local information of what's happening in my plane, I get a big conclusion about the group action. All right. Okay, and I chose this one first because it's kind of doable right at the beginning, and two, because my motivation is eventually to be something about understanding fixed points of action, you know, of group elements. And so that's why this will reappear again. Okay. So let me write down the thing I said before. Here's another proposition that you can prove, again, just from the actions. So same setup. I have a G acting on my bifoliated plane. That's a non-trivial Anosov-like action. If the plane is not skew, then there exist adjacent lozenges. Okay, so in the case 3 of our trichotomy, you always have this local picture, in fact, and therefore the set of non-corner fixed points is dense. Okay. And kind of the proof idea, without an actual proof, is that, you know, by the trichotomy theorem, you know that there are some non-separated leaves. Okay. So you have to somehow argue that, okay, you know, you can find adjacent non-separated leaves as soon as you have some. And then you want to argue that, well, if I have 2 non-separated leaves, then they actually belong to lozenges. These are sides of lozenges. Okay. And one of our other axioms says that, well, there is some element that fixes both of these non-separated leaves, so it has some fixed points on it. All right. And you want to show that actually these fixed points become corners. Okay. And this proof actually shows something more general. More generally, you can show that if some element of your group fixes at least 2 points in the plane, then these points are connected by a sequence of lozenges that either share corners or sides. So then there is, I'll say, a connected union of lozenges that are invariant, where each one is fixed by G, containing both points. Okay, G is not the identity, is our standing assumption. Right. Okay, so this is sort of the babyest case of this more general result, which says that, okay, I have 2 fixed points on adjacent non-separated leaves, then I see this structure where their lozenges comment both. And this is a, oh, yep.
So you suggest that, did you prove Sergio's theorem?
This is Sergio's theorem, yeah. So this is what the comment I was about to give. So in the Anosov case, this is an argument due to Sergio Fenley, but his case is, his proof is basically occurring in the orbit space, and so you do not have to do more work. I mean, you have to check that the outline still works here. But you follow your nose, and it uses basically only the dynamics of the action. So what are you supposed to do? You have 2 fixed points, right? I don't know. I'll give a 1-second sketch of this. You know, I fix 2 leaves here. I fix some other 2 leaves here. The leaves that are preserved do not intersect. And I want to understand, like, what is the action? So there's some, if these are the red ones, there's some red leaf in between that doesn't intersect any of them, and I want to sort of see its image under G, and where if I iterate G, this will limit onto something that has to make a perfect fit in one direction or the other, and you build the chain out kind of inductively. Oh, there's work to do. It's non-trivial. Yeah. I thought of proving this, but it will take me the rest of the time, so I'm going to not prove it. It's, that one's. I'm going to prove only the easy things. That's the deal with giving a talk. Okay. But I want to quote this a little bit later. So let me just say, Henley for Anosov flows. Okay, what's next on my agenda? Okay, so for the remainder of our time today, I want to prove, hopefully I'll get all the way there, some evidence towards this theorem being true, that if I know the set of elements that acts with fixed points in one of these Anosov-like actions, I know what the plane is. So let's prove the most basic question in that direction. So here's our next goal. I'm going to call it the skewedness proposition. Okay, and it's a baby case towards the thing called theorem up there. Okay, so suppose I have two different group actions. These are actions of my group G, Anosov-like, non-trivial, so my plane isn't trivial, on some biofoliative planes. Okay, and suppose I know the same set of elements, just group elements, acts with fixed points, and P rho 1 equals curly P, that's a curly P, of rho 2. Okay, then the first plane is skew if and only if the second plane is skewed. Okay, so the first thing you would want to check to see if these planes are homeomorphic with their bifoliations or not. Okay, all right, so hopefully let's try and prove this in the end. At least you'll see some evidence for that being true. And how we go about it. This is actually a lemma on the way to it that you have to deal with. Okay, so there's our goal. And I need some more tools. And somehow, what do I have to do? Is I have to somehow say something about the structure of these foliations, knowing from what group elements have fixed points. Okay, so the idea is we're going to talk about whether fixed points have their leaves intersecting or not. Okay, so our tool, here's a definition. So I'm going to suppose, I don't know, A and P and B and P. So P is either one of my planes with either one of my group actions. Consider either one just fixed. And this is fixed by the action of some G. Let's suggestively call this alpha and rho beta, so you can remember who's fixing who. Okay. We say A and B are totally linked. Okay, if here's A, here's B. I want the blue foliations, the red foliation of A to intersect the blue leaf of B, and the red leaf of B to intersect the blue leaf of A. So these, the leaves through them intersect as much as possible. All right. Partially linked. if you can guess what this is going to be. All right, I don't care. Remember, I'm intentionally using red and blue for plus and minus because all I want to say is that these are two different foliations. I don't really care which one's labeled which. Partially linked if one leaf of one intersects one leaf of the other, and unlinked otherwise. All right, so wherever these are going in my plane, they don't intersect at all. Okay, some things that can happen with topology of leaves. All right. And the lemma is that you can detect these kind of configurations by knowing which elements have fixed points or not. Okay, so lemma has a few parts. Let me state a first easy part to prove. If A and B are totally linked, okay, with this setup, all right, then for any powers, positive or negative, I could take any iterates of these elements. So I'm going to iterate, what I call it, alpha to the n, composed with beta to the m, all right? This has a fixed point. So what is my notation for that? That's a thing that's fixed by my action. Let me just even prove this before I state a second part so you can see how this goes. This one's easy. Okay, so let's prove one. Okay, I have this configuration. All right, and I know my dynamics of alpha and beta are, contracting one direction, expanding another direction on these two leaves. That's axiom 1, right? And someone gave me powers. I didn't get to choose positive or negative, so I'm just going to randomly choose whether you're contracting or expanding here. Great. I chose one of them. All right. So with this choice that I made, let's see the direction that this iterative alpha and that iterative beta go as I iterate is they agree on red leaves. They will all live it down onto this one. But there's some disagreement on the action on blue leaves that pass through this box. And so that's the one that I'll focus on. All right, so consider the set of all blue leaves that passes between the two that I drew. And let me call this, I don't know, interval I in the leaf space of one of my foliations. I don't know, maybe it was F plus, it happened to me. All right, what do I have is that alpha, which one I'm supposed to do first? Beta to the m, rho beta to the m of I is a subset of I. Oops, I did this in the inverses. Oh no, I should have picked the ones that were going in the same direction. I'm bad at doing things with direction on the board. Yes, I should have picked the one that were going in the same direction. No.
And negative doesn't work?
Yes, yeah. So I have to choose the right negative or positive depending on who's going where. Here I should do alpha first, and then I do this one. So, wait a minute, I've done something fishy.
So just take negative powers and then you can switch the order of alpha and beta.
Oh, good. Phew, good. Yeah, that's fine. Okay, great. So this is fine. This is equivalent to saying, yeah. Good. Rho, alpha. These things are hard to do. When I make a random choice, it's like I get one shot to do it right. So let's do rho alpha to the minus ni. And no. If I do, hold on. I need, good. I should have chose this direction and then done alpha minus and then beta plus. Whew. All right, sorry. There's always one that works. Now you know this wasn't rehearsed, and I was like, I'll give you a representative case. Here's I in the leaf space of F minus. Great. And now if I do rho, no, I've done something strange here.
For this one, you want to look at the positive of beta and the negative of alpha.
Yes, but it should be for any iterate. Oh no, you have to choose whether they're positive or not. Yeah. Okay, my bad. All right, it's because I wrote the statement wrong that I was no good. I don't get to, because here's somewhat, I wrote the statement wrong is what I did. Yes. Now we all know why I'm confused. There's a positive versus negative linking issue here. All right. So I can write a version of it this way, which says that for all alpha in, say, Z, yeah, okay, fine. No, it depends on, all right. There's two possible configurations. One is it depends on the dynamics of what they do. So maybe I'm going to normalize so that you attract the red leaves are contracting. All right. Okay. So. All right. Now I can say for all alpha, beta, and N or something like this, what I want them is to disagree. Sorry, and if I compose this has a fixed point. Okay. Great. Okay, so now I can just run the argument I tried to do before, but I was sunk. So what do I want is I need to just pick the powers of alpha and beta to start up to replacing them with their inverses so that they contract versus expand the same foliations. That was what was important. All right, and so now I consider either one set of intervals in the leaf space. Maybe I consider this I in the leaf space of F, whichever one it was. I apply some giant positive power of alpha. Maybe alpha was this one. It takes I into itself. And that's the same for any positive power. I apply some giant positive power of beta. I still take I and therefore a subset of it into itself. All right, so by Brouwer fixed point theorem, this is an interval in the leaf space. There exists some fixed leaf in I, and by our axiom 1, there is a fixed point on that fixed leaf. All right, good. So assuming that I've chosen the power of alpha and beta so that they contract the same foliation versus expand the same foliation, this works. Okay. I want to distinguish this from, say, the partially linked versus unlinked case. Okay. All right, so let's do, I don't know, let me write the unlinked case. My claim is that two fixed points are unlinked if there exist so that whenever I take a power, I have no fixed point. And this one is, I believe this one should be, let's hope this argument works the way I have it in my head. Should be independent of whether I first, swapped beta with its inverse or something to make it agree with alpha or not. All right. Okay, so what's my picture here? I have something unlinked. I know. I don't know how it's configured. Okay. And here, the way to argue this nicely is another tool which I'm going to have to hand wave at a little bit, but it's the idea that you can compactify your plane by a sort of boundary of ends of leaves at infinity, cooked up appropriately so that the obvious things happen in these cases. So, here my boundary is like these two diagonal strips. Here I would really see a boundary at infinity of the plane. I'll have like intervals worth of endpoints of leaves and intervals worth of endpoints of leaves and an extra point in the closure of that, completing this to a circle. And here I can do a similar thing no matter what happens, saying endpoints of leaves up to equivalence and take some completion. So this idea goes back to Sergio Fenley, but there's an older version of this, but when you have only a single foliation, not two transverse ones, in an old paper of Mather. Christian Bonetti has a new sort of nice exposition where he studies the dynamics on the action of this circle at infinity. It's a very natural thing to do. Okay, so this will help me situate my plane inside of some space I've compactified. And now I want to figure out what goes wrong here. Okay, so I'm going to argue by contradiction what would happen if this had a fixed point under all iterates. So I'm going to divide my circle at infinity in half now, and this will play the role of the interval in the leaf space I took before. I'll take all the leaves with endpoints in this half of my circle. So now let's call this one I. And what happens to I when I apply first some huge power of b, of beta? All right, well, it'll go somewhere. I don't know which one was the attracting fixed point or not. Let's say maybe this was the expanding leaf or something. So I will get attracted. Whoop. Now I have an induced action on the circle where the dynamics are kind of the obvious things you would think that as leaves get pushed down here, their endpoints get attracted onto this one. So if I take an enormous power of, oops, I was supposed to do alpha first. Well, never fear, I'll relabel them different. Just to save myself which one. So I'm supposed to do alpha first. I apply some huge power of alpha. I end up over here. And now I apply some huge power of beta. Maybe the red ones are both attracting points like before. No matter for this argument, I could end up here, it would be just fine. I apply some huge power of beta, and let's see, that's now a repeller on the boundary at infinity, and I end up somewhere very close to the attractor of beta that sits outside, that sits inside of I here. Okay, so this tells me that I have, if I had a fixed leaf, its endpoint would be some, I should fix a leaf that has an endpoint somewhere in there. Or maybe I fix no leaves at all. All right. And then you want to run the same argument with an interval that looks instead like this. Let's call this one J. And if I do the same thing, I apply first some, I'll do the inverses now. I'll do some giant negative power of J, followed by some giant negative power of alpha to see what would happen to the inverse of this. And now what am I supposed to do? Giant negative power of beta will end me up over here. Giant negative power of alpha will go onto, this is now the retractor, going to end up over here. it's taken into itself. Okay. So should I have some leaves, if this thing didn't have just kind of like translation dynamics across the plane, there was really leaves that were fixed there, the only endpoints, their endpoints can only land in here and here. Right? These are the sets of endpoints of leaves where I will see fixed points. Everyone else gets moved a distance. Okay. So if there is a fixed leaf, well, at least one of them has an endpoint in here and some other one has an endpoint in there. By this remark about if I see some fixed leaves and therefore fixed points, they're in some connected union of lozenges together, right? Either I'll see a single leaf that connects these, or maybe some various lozenges here, kind of like long and skinny, that connect them. All right. But no matter what, I'll always see some leaf of my foliation going from one of these subintervals to the other. And as n and m go to infinity, right, the leaves that I see will approach a attracting and a repelling point of alpha and beta. The endpoints of these so here I should add a hypothesis that I forgot to write down. If these are unlinked and not corners, then we win. All right, because I conclude as I take a sequence of these, right, leaves that have endpoints witnessing these two places I'm supposed to go, they'll limit to something that almost but not quite intersects these two fixed points. Okay. Or corners of some lozenge. I'll see a perfect fit here and here. All right, I realize I had to hand wave more than I wished for this, but hopefully what I did is give you a flavor of a bunch of tools you throw at this, of see what happens at infinity, find a sequence of leaves, think about its limits. Do you come up with corners? What kind of topological stuff apply inside of the plane? Okay, so I didn't quite get to what I wanted to prove, but let me finish what we have here. I have something that if I'm trying to decide between whether two non-corner points, I have a dense set of non-corners, I'm trying to decide whether they are totally linked or unlinked. I can do that just by checking what happens in my sets of elements that have fixed points. All right, if I know these things as sets, I can check, well, what about all of these powers versus not, and see who lands in my set or not. Okay, so what I'll start with next time, so that we don't run into lunch, is to just use this linking type criterion to finish our goal and then give a step towards the proof of the theorem and hopefully state some open questions at the end. All right, thank you.
Quick question.
We can ask me over lunch. It's great. Great.